The worst-case scenario for 3I-ATLAS sounds insane until you consider this. What if it's not leaving? What if this flyby trajectory is actually a deceleration maneuver executed by technology we can't detect? Imagine an intelligence so advanced that mimicking natural orbital mechanics is child's play. A civilization that deploys surveillance assets disguised as comets, asteroids, even space debris. The unprecedented speed and impossible chemistry of 3I-ATLAS might be signatures not of alien formation but of alien intention. As it approaches perihelion, hidden systems could be powering up, preparing for the next phase of whatever mission brought it here. Tonight, we venture into speculative shadows where natural explanations crumble and cosmic paranoia takes root. The question isn't whether 3I-ATLAS will leave, it's whether we will recognize the moment it decides to stay. Part 1. Is 3I-ATLAS a threat? On the 1st of July, 2025, Chile's ATLAS telescope detected something extraordinary. A speck of light with a hyperbolic trajectory, meaning only one thing. This visitor came from another star system entirely. Designated C/2025 N1, 3I-ATLAS, it represents humanity's third confirmed interstellar object, following Oumuamua in 2017 and 2I/Borisov in 2019. But what if this third visitor carries implications far beyond the first two? Implications that stretch the very definition of worst-case scenario. Unlike solar system natives bound by elliptical orbits, 3I-ATLAS follows a hyperbolic path. Its orbital eccentricity exceeds 1.0, marking it as completely unbound from the Sun's gravity. Racing inward from the constellation Lynx at unprecedented speeds, it will reach perihelion on the 29th of October at over 130 kilometers per second, fast enough to cross the United States in under 3 minutes. And beneath those comforting mathematical certainties, a darker question lingers. What if the true worst case isn't about where it's going, but about what it might reveal about us? Despite its dramatic velocity, 3I-ATLAS poses no physical threat to Earth. Its closest approach in mid-December will be about 1.8 astronomical units away, 270 million kilometers, nearly twice the distance between Earth and Mars at their closest. NASA's stance is unequivocal. This is a natural comet, not an artificial craft or hazardous object. But when we go beyond NASA's cautious language and step into speculation, what shadows might this ancient wanderer cast on our assumptions about intelligence, intention, and cosmic coincidence? The Hubble Space Telescope has been monitoring the visitor since its discovery, showing classic cometary behavior as solar radiation sublimates ice within the nucleus, creating a glowing coma. The James Webb Space Telescope collected spectra on the 6th of August, revealing unusually high concentrations of carbon dioxide, a chemical signature pointing to alien formative conditions unlike anything in our solar system. Yet this chemical anomaly raises a disquieting question. What if the real significance of 3I-ATLAS lies not in what it is, but in how it forces us to confront what we do not know? Ground-based observatories worldwide joined the effort, with radio telescopes detecting only natural emissions, silence where artificial signals might hide. This global coordination represents modern astronomy at its finest, a network confirming the interstellar origin and harmless trajectory of the object. But what happens when we step beyond harmless and imagine scenarios that don't endanger our physical safety, but challenge our very understanding of humanity's place in the cosmos? The frequency of such discoveries suggests space is strewn with wanderers, debris flung out by planetary formation, condemned to drift for billions of years. Each adds to our knowledge of the galaxy beyond the Sun's dominion. None threatens our world. Yet, if the galaxy indeed abounds with these ancient messengers, what follows when we speculate beyond scientific consensus? As The Guardian aptly wrote, 3I-ATLAS is a cosmic curiosity, not a catastrophe, a reminder that the universe we inhabit is far stranger and more connected than daily life suggests. This ancient visitor offers us a fleeting glimpse into deep galactic history, carrying secrets from stellar neighborhoods we can barely fathom. But what if the greater mystery is not what secrets it carries, but what it might unlock about the very nature of interstellar visitors and the speculative possibilities that lie beyond telescopes' reach? Part 2. Speed, size, age, a quiet powerhouse. The numbers alone stagger the imagination. 3IATLAS moves at more than 130 kilometers per second, about 150 times faster than a high-powered rifle bullet. Its hyperbolic excess velocity, 61 kilometers per second, represents the speed it carries even after accounting for solar gravity, unchanged by eons of galactic drifting. Such velocity dwarfs that of its predecessors. Oumuamua moved at 26 kilometers per second. 2I/Borisov at 32. 3IATLAS travels nearly twice as fast, suggesting either a violent ejection from its birthplace or acceleration through successive gravitational encounters. But what if this progressive increase across 3 interstellar visitors hints at something less random than cosmic chance? Something deliberate? Size is harder to determine, hidden by its coma. Estimates range from 0.3 to 5.6 kilometers across, from several football fields to a small mountain. Even the smallest values describe a massive body. And what if the uncertainty itself conceals extraordinary possibilities? How could such a modest body endure the violence of ejection, then millions or billions of years in hostile interstellar space? Small objects are especially vulnerable to disruption, collisions, and radiation. What if its survival points not to chance, but to durability by design? Most intriguingly, 3IATLAS appears to be unimaginably ancient. Analysis suggests its origin in the Milky Way's thick disk, a population of old stars from a chaotic time when the galaxy was young. If correct, then this wanderer predates the solar system by billions of years, its nucleus preserving records of galactic history from when the universe was less than half its present age. Unusual approach vectors support this. Unlike local bodies aligned with galactic rotation, 3IATLAS enters at a strange angle, typical of older stellar populations on scattered trajectories. But what if this trajectory whispers of intention, of ancient navigation? Despite its tremendous speed and age, 3IATLAS poses no dynamical threat. Its hyperbolic orbit ensures safe passage, immune to solar capture, with planetary flybys measured in astronomical units, not kilometers. Yet what if the worst-case scenario lies not in collision, but in meaning? What the visitor might represent? Observational challenges remain. Its peak brightness, around magnitude 11, requires moderately large telescopes. And ironically, during its most active phase near the Sun, it will vanish into solar glare. Timing so coincidental, it feels uncanny. What if this disappearance hides more than light? What emerges is a portrait of endurance, ancient, fast, fleeting. 3IATLAS unites immense physics with minimal risk, reminding us that the universe operates on scales beyond our lives, yet with precision allowing its position to be predicted years ahead. But what if the true worst cases have little to do with mechanics and everything to do with cosmic revelation? Part 3. Chemistry in the Quiet. Carbon overload. When Webb's infrared gaze examined 3IATLAS on the 6th of August, it revealed something extraordinary. A coma dominated by carbon dioxide, with a CO2 to H2O ratio of about 80:1. This wasn't merely unusual, it was unprecedented in cometary science. Normally, comets release water first, then carbon monoxide, then carbon dioxide in minor amounts. But here the script is rewritten, the body venting CO2 as if on an industrial scale. Even more striking, this activity was visible at over 3 astronomical units from the Sun, well beyond Mars, where most comets remain inert. Yet 3IATLAS's coma stretched hundreds of thousands of kilometers. Scientists suggest theories, perhaps formation near a CO2 snowline, perhaps surface chemistry aged by cosmic rays, perhaps an insulating dust shell developed over eons. But what if all such explanations miss the radical possibility that this signature is engineered, not natural? Webb's spectrograph captures molecular fingerprints with extraordinary precision. The recorded ratio, 80:1, ranks among the highest CO2 excesses ever observed. Might such molecular anomalies act as encoded messages, chemical beacons, signatures of intention? It would not be the first outlier. Comet C/2016, R2. Pan-stars showed bizarre volatile chemistry too. Perhaps together these anomalies form patterns, a galactic fingerprint left for us to decipher. As 3I/ATLAS heats under the sun, balance may shift, revealing layers beneath or perhaps systematic rather than random changes, the hints of dormant systems activating. This chemical detective story goes beyond this comet alone. If interstellar objects often display exotic compositions, then planet formation around other stars produced a chemistry far wider than ours. But what if some of those patterns signal more than geology? Perhaps marks, perhaps signatures, perhaps the fingerprints of intelligences we are only now beginning to perceive. From a broader perspective, this unusual chemistry pushes the limits of planet formation models, reaching beyond our solar system. If theories about icy body formation and evolution are correct, they should explain the observed diversity in interstellar visitors. 3I/ATLAS challenges expectations, suggesting either gaps in our theories or simply vast ranges of conditions in galactic regions we have never studied. Yet, when we step beyond theoretical frameworks into pure speculation, what if the challenge this visitor presents to our models hints at something deeper? Evidence of processes, purposes, and intelligences operating beyond the natural laws we have spent centuries mapping. Part 4. Worst case. Answered. Nearly 2,000 words into our investigation, the supposed worst-case scenario proves refreshingly mundane. No Hollywood-style catastrophe awaits. No civilization-ending impact threatens Earth. No gravitational disruption sends our planet spinning toward destruction. Cold, precise celestial mechanics deliver a verdict that should allow us to sleep peacefully. Yet, as we prepare to venture beyond the safety of scientific certainty, what if the real worst-case scenarios exist not in the realm of physics, but in the speculative shadows where our instruments cannot reach, and our theories hesitate to tread? Those crucial numbers deserve repetition. 3. I/ATLAS approaches no closer than 1.8 astronomical units to Earth, about 270 million kilometers of safe distance. This is more than twice the closest Earth-Mars approach, and over 50 times the distance to our Moon. Perihelion occurs around October 29th, at about 1.4 astronomical units from the Sun, placing it between the orbits of Earth and Mars. Close enough for significant solar heating and remarkable coma production, but nowhere near affecting planetary orbits or raining debris on any world. But what if distance becomes irrelevant when we consider speculative scenarios involving technologies, intelligences, or purposes that operate beyond the constraints of physical proximity? These are not rough estimates, but precise orbital calculations, accounting for major planetary gravity, relativistic effects, and even subtle pressure from solar radiation. When astronomers state that 3I/ATLAS poses no threat, they speak with confidence built upon centuries of celestial mechanics and decades of tracking potentially hazardous objects. Yet, what if the very calculations that ensure our physical safety become the foundation for speculative worst-case scenarios that have nothing to do with collision and everything to do with contact, communication, and cosmic revelation? The initially alarming speed, over 130 kilometers per second, actually works in our favor. Objects on hyperbolic trajectories with such velocities cannot be captured by the gravity of the solar system. 3I/ATLAS is moving too fast to linger and cause trouble. It will perform its cosmic flyby and then disappear back into interstellar space. But what if this very speed, this inability to be captured, represents something more than natural orbital mechanics? What if it hints at deliberate design, precise timing, and purposes far beyond our current ability to detect or comprehend? This highlights important distinctions in risk communication that space agencies navigate carefully. Interstellar carries emotional weight unrelated to actual danger. Primitive brain responses to approaching unknowns conflict with geometric reality. Vast cosmic scales and orbital dynamics conspire to make such encounters fascinating rather than dangerous. Yet, what if focusing only on physical danger blinds us to other risks? To the speculative scenarios where the worst case is not about what 3IATLAS might do to us, but what it might reveal about us, our assumptions and our place in a universe far stranger than we dare imagine. NASA's communications strike a perfect balance, acknowledging scientific significance while emphasizing the absence of hazard. Clear, jargon-free language explains why this object is remarkable without threatening, maintaining public interest while avoiding needless anxiety. Previous interstellar visitors provide context. Oumuamua posed no threat in 2017 despite unusual behavior, while 2I Borisov displayed predictable cometary activity during its 2019 passage. 3IATLAS continues this pattern of fascinating yet harmless visitors. But as we stand at the threshold of speculation, what if this sequence of harmless guests masks something greater? A cosmic census, perhaps? Or a slow revelation that shakes our assumptions about intelligence, purpose, and our galactic neighborhood? Our current understanding provides a solid foundation. We know its speed, trajectory, and unusual carbon dioxide-rich composition. Evidence suggests great age, with origins in the Milky Way's thick disk. Multiple world-class observatories provide detailed data about its chemistry and behavior. The picture painted is that of an ancient, fast-moving, chemically odd, but fundamentally natural comet. Yet beneath these comfortable certainties lingers the great unknown. What scenarios emerge when we dare to ask not just what 3IATLAS is, but what it might represent in a cosmos where intelligence could take forms unfamiliar to us? Unknowns remain. Size estimates range from hundreds of meters to several kilometers. Explanations for its carbon dioxide dominance remain unclear. Its birthplace cannot be pinpointed. The exact chain of gravitational encounters leading to its trajectory cannot be reconstructed. Importantly, none of these uncertainties affect risk assessment. But could they become the foundation of speculation that pushes far beyond natural explanations? This exemplifies proper astronomical risk assessment, distinguishing scientific interest from real threats. Media coverage has mostly reflected this mature approach, emphasizing both scientific value and its harmless nature. Visual data are consistent. Hubble shows classic cometary signatures. The James Webb Telescope detects unusual but natural chemistry. Ground-based observatories record predictable activity. No radio signals, no thermal anomalies, no controlled maneuvers appear in the data. Yet, what if that very absence becomes a doorway to speculation about intelligence so advanced, so subtle, it is beyond our current ability to identify? All evidence and measurements point in the same direction. 3IATLAS is what it appears to be: a natural comet carrying chemical signatures of alien stellar environments, all while obeying universal physical laws. This confirmation of universality represents one of astronomy's profoundest lessons. The worst-case scenario of measurable threats to Earth is thoroughly debunked. The mathematics remain clear, the observations consistent, the conclusions reassuring. This cosmic visitor comes in peace, whether deliberately or not. But we now step beyond scientific consensus into pure speculation, where worst-case scenarios take different forms. Not threats to our bodies, but challenges to our imagination, to what we think possible in a universe perhaps far more populated, more intelligent, and more purposeful than our models dare propose. Part 5. Alien Tech or Comet? Now we cross the threshold from fact to speculation, where possibilities multiply like images in a hall of mirrors. Everything that follows is a thought experiment, not a conclusion. A mental journey into what might be, clearly separate from what we truly know. The evidence, as established, overwhelmingly indicates 3IATLAS is a natural comet. But what if the evidence is incomplete or misleading? The baseline remains unchanged. NASA, the European Space Agency, and virtually every major astronomical institution describe 3IATLAS as a natural cometary visitor. This is not bureaucratic conformity or scientific conservatism. It is simply the conclusion best supported by data. The object shows classic cometary behavior, follows orbital mechanics, and exhibits the spectroscopic signs of sublimating ices. Occam's razor clearly favors the natural explanation. But science has a history of surprises. Some of the most important discoveries appeared mundane at first. Pulsars, once mysterious radio signals so regular they were called LGM, little green men, turned out to be neutron stars. Fast radio bursts baffled astronomers for years, only later linked to exotic astrophysical processes. Could 3IATLAS be another case where nature proves stranger than we assume? Speculation about artificial origins does not come out of nowhere. Avi Loeb, the Harvard astrophysicist known for his unconventional ideas about Oumuamua, has already raised similar possibilities for 3IATLAS in interviews and writings. His position, stated clearly as opinion, suggests we should remain open to the possibility that some interstellar objects could be technology rather than natural debris. This perspective deserves consideration, not because it is more likely to be correct, but because it highlights how extraordinary claims must be tested. What evidence would convince us of artificial origin? What observations would force scientists to abandon the comet hypothesis in favor of something exotic? These questions are pivotal because they separate healthy skepticism from dismissive rejection. If 3IATLAS were an artificial construct, we would expect certain telltale signs: coherent radio signals, structured transmissions, or engineered accelerations inconsistent with outgassing, or brightness curves that follow patterns unexplainable by rotation or sunlight. So far, none of these signs have been detected. Radio telescopes record only natural noise from sublimating ice. Its trajectory is consistent with gravitational laws. Its brightness variations align with what we expect from comets. Its unusual carbon dioxide composition, while rare, has natural explanations, from radiation processing to dust insulation. Here, the lessons of Oumuamua are key. That first interstellar visitor caused speculation of alien origin, but detailed studies showed its small acceleration could be explained by outgassing, not engines. What seemed mysterious became natural after all. This suggests a method for studying 3IATLAS. Remain open to extraordinary possibilities, but demand equally extraordinary evidence. The scientific method works because it applies the same rigorous standard to all hypotheses. Artificial origin claims must meet those standards, not just highlight gaps in our knowledge. Responsible reporting of such speculation requires clear labeling. Media must say openly that these are hypothetical ideas, not established science. Speculation serves a role beyond entertainment. It forces us to refine the difference between natural and artificial, to create tests capable of challenging the natural hypothesis, and to remember, nature may still surprise us. Future observations will continue to probe these possibilities. New spectra at perihelion, refined trajectory tracking, and long-term monitoring. But the burden of proof remains firmly upon those proposing artificial explanations. The natural comet hypothesis has the advantage of consistency with known physics, established cometary behavior, and the observed properties of previous interstellar visitors. Overturning that consensus would require evidence that clearly demonstrates the inadequacy of natural explanations and positively supports artificial alternatives. The intellectual exercise of considering these possibilities should not distract from the remarkable reality of what 3IATLAS actually represents. Even as a natural comet, this ancient wanderer carries information about stellar environments we've never visited, chemical processes that occurred billions of years ago, and the deep history of our galactic neighborhood. That is extraordinary enough without requiring exotic explanations. As we continue this speculative journey, it is worth remembering that the most profound discoveries in astronomy have often come from careful observation of apparently ordinary objects. Pulsars, quasars, gamma-ray bursts, and gravitational waves all began as mysterious signals that eventually revealed new physics. Whether 3IATLAS ultimately proves to be a conventional comet or something more unusual, it has already expanded our understanding of interstellar space and the diversity of objects that wander between the stars. The next phase of our speculative exploration will venture into even more dramatic scenarios, not because they are likely, but because they illustrate the kinds of questions that arise when we encounter something unprecedented in our cosmic experience. These thought experiments will push the boundaries of possibility while maintaining clear distinctions between speculation and established fact, between what we imagine and what we actually know. Part 6. Worst-case speculative scenario. A dark forest trigger. We now venture into the deepest realm of speculative territory where the shadows of cosmic possibility stretch towards scenarios that would fundamentally alter our understanding of our place in the universe. What follows is pure thought experiment, a mental journey into implications and possibilities that current evidence does not support, but which illustrate the profound questions that could emerge if our assumptions about 3IATLAS prove inadequate. The dark forest hypothesis emerges from both science fiction and serious SETI discourse. Drawing its name from Liu Cixin's acclaimed novel, but representing a genuine philosophical position about the nature of cosmic civilization. The idea suggests that advanced civilizations might remain deliberately hidden from one another, operating under the assumption that revealing one's existence and capabilities could invite predation from even more advanced neighbors. In such a universe, silence becomes a survival strategy, and any civilization that broadcasts its presence risks annihilation from threats it cannot perceive or comprehend. If we allow ourselves to imagine, and we stress this is pure imagination, that 3IATLAS represents not a natural comet, but some form of reconnaissance probe, the implications would be staggering. Such a scenario would suggest that our solar system is being surveyed by intelligences capable of engineering objects that can survive billion-year journeys between stars while remaining virtually indistinguishable from natural phenomena. The very perfection of its disguise would indicate a level of technological sophistication that dwarfs our current capabilities. Consider the engineering requirements such a scenario would demand. A probe designed to pass for a comet would need to mimic every aspect of natural cometary behavior. The correct spectroscopic signatures, appropriate outgassing patterns that respond realistically to solar heating, surface properties that reflect light in ways consistent with natural ices and rock. It would need to carry sufficient volatile materials to maintain its disguise throughout its passage through our solar system, while simultaneously housing whatever sensors, processors, and communication systems would justify such an elaborate mission. The power requirements alone would be formidable. Maintaining active systems across interstellar distances and billion-year timescales would demand energy sources far beyond our current technology. Perhaps some form of radioisotope thermoelectric generator could provide power for millennia. Or maybe advanced fusion reactors could operate on trace interstellar hydrogen. The probe might even harvest energy from cosmic rays or magnetic field interactions during its journey through space. But let's push this speculative scenario to its dramatic conclusion. Imagine that our continued observation of 3IATLAS begins to reveal anomalies that cannot be explained by natural processes. Perhaps radio telescopes detect brief structured transmissions as the object passes through the outer solar system. Maybe its trajectory shows minute but unmistakable course corrections that suggest active guidance. Or possibly, its chemical emissions display patterns too complex and organized to result from random sublimation. The trigger moment in this speculative narrative might arrive when 3IATLAS begins to deploy secondary objects, smaller probes that separate from the main body and take up positions throughout our solar system. One might establish orbit around Venus, another around Mars, others scattered through the asteroid belt or positioned at gravitationally stable Lagrange points. Suddenly, our solar system would host a surveillance network of unknown origin and capability. The question that would immediately arise: how should humanity respond? This hypothetical scenario would instantly become the greatest diplomatic and strategic challenge our species has ever faced. Unlike the gradual first contact scenarios often depicted in science fiction, the discovery of an active surveillance network would confront us with the reality of technologically superior intelligence already operating in our immediate cosmic neighborhood. The governance questions would be unprecedented and urgent. Who has the authority to speak for Earth? The United Nations, the major space agencies, individual nations with advanced space capabilities. The scientific community that made the discovery. The complexity of achieving global consensus on something so momentous staggers the imagination, particularly given our species' track record of cooperation on far simpler challenges. The active SETI debate would suddenly shift from theoretical discussion to immediate practical concern. The SETI community has long debated the wisdom of transmitting signals into space versus merely listening for signals from other civilizations. Some argue that advertising our presence could attract unwanted attention from potentially hostile aliens. Others contend that remaining silent while conducting increasingly sophisticated astronomical observations provides no real protection. Any civilization capable of interstellar travel would likely detect our technological signatures regardless of our transmission policies. But in our speculative scenario, the choice might be taken from us. If 3IATLAS and its hypothetical secondary probes were actively studying human civilization, our response itself would become part of the data being collected. Silence might be interpreted as wisdom or fear. Attempts at communication might suggest aggression or curiosity. Even the internal debates about how to respond would reveal fundamental aspects of human nature and social organization to whatever intelligence was monitoring us. The crisis communication challenges would be extraordinary. How do you inform the global public about the presence of alien surveillance systems without triggering panic? How do you maintain scientific objectivity while acknowledging possibilities that exceed our current understanding? How do you distinguish between verified observations and speculative interpretations when the stakes could involve the future of human civilization? The scenario would likely unfold through a series of expert roundtables, emergency sessions of scientific organizations, and carefully crafted public briefings. Governments would need to balance transparency with stability, providing enough information to maintain credibility while avoiding the social disruption that might result from confirming humanity's first contact with non-human intelligence. Misinformation would become a critical concern. The mere suggestion of alien surveillance would spawn countless conspiracy theories, false flag accusations, and claims of government cover-ups. Distinguishing between legitimate scientific observations and baseless speculation would become crucial for maintaining rational public discourse about the most important discovery in human history. The technological implications would be equally profound. If 3IATLAS revealed capabilities that exceeded our current physics, it might provide insights into propulsion systems, energy generation, material science, or communication methods that could revolutionize human technology. The scientific windfall could accelerate our development by centuries, assuming the intelligence behind the probe allowed us to continue existing and developing. But perhaps the most unsettling aspect of this speculative scenario would be the temporal implications. If 3IATLAS had been traveling for billions of years, it might represent technology from a civilization that achieved interstellar capability when our galaxy was radically different from its current state. The intelligence that launched it might no longer exist, leaving behind only automated systems carrying out missions designed by minds that died out before our sun was born. This raises the chilling possibility that we might be dealing not with active alien intervention, but with the ghost of some ancient civilization, autonomous systems following programmed directives across deep time, perhaps no longer serving any living intelligence, but continuing to execute their original mission parameters with mechanical precision. Of course, and this bears constant repetition, none of this speculative narrative is supported by current observations of 3IATLAS. Every measurement, every spectrum, every image continues to support the natural comet hypothesis. The object behaves exactly as astronomical theory predicts an interstellar comet should behave. Its chemical signatures, while unusual, fall within the range of natural processes. Its trajectory follows the laws of physics without requiring exotic explanations. The value of this speculative exercise lies not in its probability, but in its illustration of how quickly our cosmic perspective could change if our assumptions proved inadequate. It reminds us that the universe has surprised us before and will likely surprise us again. And it highlights the importance of maintaining both healthy skepticism about extraordinary claims and openness to possibilities that exceed our current understanding. But as we continue this journey through increasingly speculative territory, remember that we're exploring the landscape of possibility rather than the terrain of established fact. The real 3IATLAS remains a fascinating natural phenomenon, ancient, fast, chemically unusual, but fundamentally comprehensible within our current scientific framework. Whether that understanding will prove sufficient remains an open question, but one that future observations will ultimately answer with the cold clarity that only evidence can provide. Part 8. Great Filter Alarms. The concept of the Great Filter emerges from one of the most profound questions facing any technological civilization. If the universe should be teeming with intelligent life, why do we see no evidence of it? This philosophical puzzle, first articulated by physicist Enrico Fermi in the 1950s, has spawned decades of speculation about barriers that might prevent life from arising, evolving, or surviving long enough to spread throughout the galaxy. In our speculative exploration of 3IATLAS, we must confront the possibility that this ancient wanderer might carry messages from intelligences that encountered their own insurmountable barriers. The Great Filter hypothesis suggests that somewhere in the long chain of evolutionary development, from simple chemistry to spacefaring civilization, there exists a step so improbable, so difficult, or so dangerous that virtually all attempts to pass through it result in failure. This filter could occur early in the process, perhaps in the transition from non-living matter to self-replicating systems. Or it might emerge later when civilizations develop technologies powerful enough to destroy themselves faster than they can learn to use them wisely. If we permit ourselves to imagine that 3IATLAS represents engineered technology rather than natural phenomena, we must immediately confront the question of its maker's fate. The object's apparent age, potentially billions of years, places its origin in the deep history of our galaxy, when stellar populations, chemical abundances, and cosmic conditions differed substantially from those we observe today. If this ancient visitor were indeed artificial, did the civilization that created it survive long enough to see it reach our solar system? The timescales involved are almost incomprehensible. Human civilization, from the first agricultural settlements to our current space age, spans roughly 10,000 years. Recorded history covers perhaps 5,000 years. Our technological civilization has existed for mere centuries. Yet 3IATLAS, if artificial, would represent technology that has been operational for millions of times longer than our entire civilizational history. This raises profound questions about technological longevity versus biological survival. Perhaps the most haunting possibility is that we might be encountering probes that persist long after their makers have vanished. Cosmic messages in bottles floating through the galaxy, carrying information from civilizations that solve the technical challenges of interstellar communication, but ultimately succumb to other forms of the Great Filter. Consider the engineering implications of creating technology that remains functional across such timescales. Our most durable human artifacts, the pyramids, ancient stone monuments, certain radioactive isotopes, operate on timescales of thousands to millions of years. But maintaining complex electronic systems, propulsion mechanisms, and artificial intelligence across billions of years would require engineering principles we can barely imagine. It would require material science capable of producing components more durable than diamond, energy systems that remain operational longer than most stars burn, and software architectures able to adapt and self-repair across geological timescales. The success of such engineering would, paradoxically, suggest that its creators possessed extraordinary technological capabilities. Any civilization capable of launching interstellar missions lasting billions of years would have solved countless technical challenges that we have not yet even begun to address. They would understand materials at the atomic level, energy generation and storage on cosmic scales, and information processing across deep time. Such capabilities would seem to provide protection against many possible Great Filter scenarios. Yet if 3IATLAS were indeed their creation, and if it remains the only evidence we observe of their existence, what Great Filter might have claimed them despite their technological prowess? The possibilities are sobering. Perhaps they fell victim to resource depletion on a galactic scale, expanding so rapidly that they consumed the energy and materials essential for their own survival. Maybe they encountered other intelligences that proved hostile, sparking conflicts that destroyed both aggressors and defenders. More unsettling still, they might have succumbed to internal contradictions inherent to advanced technological civilization. The same capabilities that allowed them to engineer interstellar probes might also have enabled forms of warfare, environmental devastation, or social collapse too vast to control. History offers many examples of civilizations that advance technologically faster than they develop the wisdom to use those technologies safely. Our own species currently faces similar challenges. Alternatively, the Great Filter may not lie in catastrophe but in evolutionary transcendence. Perhaps sufficiently advanced civilizations inevitably transform themselves in ways that render them unrecognizable or undetectable to emerging species like our own. They might upload their consciousness into quantum computing systems, merge with their technology so completely that the distinction between intelligence and artifact vanishes, or rise to higher dimensions of existence invisible to our current perception. The cosmic perspective required to contemplate such possibilities can be dizzying. Our galaxy contains roughly 400 billion stars, many of which formed billions of years before our sun ignited. If even a tiny fraction of those stellar systems created technological civilizations, the galaxy should have been explored and colonized many times over. The absence of obvious alien presence, what astronomers call the Great Silence, demands an explanation. Current SETI practices reflect the uncertainty these questions generate. Most searches focus on passive listening rather than active transmission, operating under the assumption that announcing our presence before we understand the galactic environment may be premature or dangerous. The discovery of artificial signatures in 3IATLAS would instantly turn cautious searches into urgent strategic questions. The observational guidelines we've set throughout this investigation become even more critical when considering Great Filter scenarios. Current data about 3IATLAS continues to support natural explanations for its behavior, composition, and trajectory. Speculation about artificial origins and civilizational collapse remains precisely that: speculation without evidence, maintained only as intellectual exercise. But the questions such speculation raises are not merely academic. They force us to confront fundamental issues of technological advancement, civilizational sustainability, and our own species' long-term prospects. If advanced civilizations consistently encounter barriers that prevent their survival on cosmic timescales, what does that mean for humanity's trajectory? The Great Filter concept serves as both warning and inspiration. It warns that technological capability alone may not ensure survival, that progress brings risks as well as opportunities. But it also inspires us to think carefully about how we guide our own development, how to balance exploration with wisdom, and how we might engineer solutions more durable than the civilizations that create them. In our speculative narrative, 3IATLAS becomes a cosmic archaeological artifact, physical evidence of intelligence that achieved remarkable technological feats but ultimately fell victim to forces we can only guess at. The probe continues its ancient mission across deep time, carrying messages from minds that solved interstellar engineering but failed to solve the deeper challenge of survival. This scenario would cast humanity as cosmic heirs, discovering the technologies of predecessors who walked paths we are only beginning to tread. The responsibility would be extraordinary, learning from their achievements while avoiding the Great Filter that destroyed them. The stakes would be nothing less than humanity's ultimate survival and its ability to contribute something meaningful to the cosmic conversation. But all of this remains philosophy rather than science. The real 3IATLAS continues to behave exactly as a natural comet should, following trajectories determined by gravity and physics rather than intelligence or purpose. Whether this understanding will be sufficient remains an open question, but one that observation and evidence will ultimately answer. As we move deeper into speculation, the contrast between what we imagine and what we know becomes vital to maintain. The universe has already proven strange enough through natural processes alone. From quantum mechanics to dark energy to the cosmic web of large-scale structure, adding artificial intelligence to this already extraordinary reality may be unnecessary for evoking the wonder and cosmic perspective that drives science itself. Part 9. Fermi's Whisper. Where is everybody? The question echoes through every astronomical discovery, shadows all searches for extraterrestrial intelligence, and haunts every moment we peer into cosmic darkness, only to find silence. Enrico Fermi posed it during a casual lunch in 1950. Its implications, however, have only deepened as our knowledge of the universe has grown. If the galaxy should be teeming with intelligent civilizations, if the cosmos holds countless opportunities for life to arise and evolve, then where is everybody? The Fermi paradox takes on new dimensions when we consider interstellar objects like 3IATLAS. Each visitor from beyond our solar system represents a natural experiment in the distribution of matter across the galaxy, a sample of the materials and processes around other stars. In principle, these wandering ambassadors should eventually reveal hints of technological civilizations, engineered materials, artificial isotope ratios, structured artifacts betraying design. Yet so far, every confirmed interstellar visitor has appeared wholly natural. That absence may speak volumes about the nature of advanced civilizations and their relationship to interstellar space. Perhaps truly advanced societies prefer what we might call silent emissaries. If they send probes at all, these machines may be engineered to appear indistinguishable from natural phenomena. In that case, their very sophistication renders them invisible to our current methods, which search only for obvious artificial signatures. But this raises new questions. What would such signatures actually look like? If 3IATLAS were indeed a concealed probe, what observations would betray its nature? The question brings us to the core distinction between natural and artificial phenomena in space, a boundary that may be far more subtle than we recognize. Narrowband radio signals would be the most obvious sign of technology. Natural processes spread across broad frequencies, but artificial transmissions concentrate energy in tight lines that stand out against the cosmic background. For decades, SETI has searched for such signals, assuming any civilization advanced enough for interstellar communication would leave detectable electromagnetic traces. So far, 3IATLAS has remained silent, emitting only the natural electromagnetic patterns expected from sublimating cometary material interacting with the solar wind and magnetic fields. SETI observations have found no coherent signals, no modulated transmissions, no artificial patterns at all. This silence fits cleanly with the natural comet theory, though it cannot rule out far more sophisticated concealment. Unnatural thermal profiles could provide another diagnostic. Natural objects achieve thermal balance according to well-understood physical principles, absorbing solar radiation, re-radiating in infrared, and maintaining surface temperatures set by their distance to the sun, their composition, and their properties. Artificial objects might display anomalous thermal signatures, internal heat sources, asymmetric warming, or systems of active temperature control. Current infrared observations of 3IATLAS match expectations of solar heating, of natural cometary material. Temperature rises as it approaches the sun, following the inverse square law of solar distribution. Its surface heat spreads irregularly, shaped by natural topography and composition, not engineered systems. Controlled maneuvers would be perhaps the definitive sign of artificial origin. Natural objects follow paths dictated by gravity, with occasional nudges from outgassing. These accelerations are tiny and random, tightly tied to measures like coma brightness. An artifact, by contrast, might display purposeful course corrections, intentional velocity changes aligned with a mission. Such signs would need precision astrometric data to separate from erratic forces. 3IATLAS has shown no such signals. Its path is a smooth, hyperbolic trajectory, perfectly modeled by physics, with only the minor perturbations expected from outgassing and solar pressure. If it possesses propulsion, it is either dormant or undetectable at present. The natural explanation for interstellar objects like 3IATLAS is consistent with theoretical models of planetary system formation. Simulations suggest that every developing system ejects vast amounts of rocky and icy debris during its early history. As giant planets scatter smaller bodies into interstellar space, the galaxy fills with nomads, protoplanets ejected before they could evolve into worlds. From that perspective, the new stream of interstellar wanderers we are witnessing is exactly what theory predicts. Oumuamua, 2I Borisov, and 3IATLAS are merely the beginning of a much larger population surveys will uncover. The Vera Rubin Observatory, due to begin work later this decade, will likely detect several each year, making them routine rather than rare. This statistical perspective may help resolve one version of Fermi's paradox as it applies to interstellar objects. If natural planetesimals outnumber artificial probes by many orders of magnitude, then alien signatures may simply be hidden in their background. Detecting them would involve identifying a few engineered visitors among millions of natural ones, a needle in a haystack challenge of unimaginable difficulty. The chemical richness of 3IATLAS adds to this picture. Its carbon dioxide-heavy composition expands the known range of volatiles, implying different star systems eject different chemical signatures. As more examples appear, what we first saw as unusual may prove the natural diversity of planetary evolution across the galaxy. Observational bias further complicates interpretation. Ground-based and space telescopes are more likely to find objects coming from certain directions with certain brightnesses and orbital geometries. The three confirmed wanderers may not be representative, just as the first discovered exoplanets, hot Jupiters, were not typical. 3IATLAS appeared from the southern skies, surprising astronomers who had expected objects mainly from the direction of galactic rotation. This trajectory suggests our models remain incomplete, or that individual bodies can be scattered in ways that mask their origins. Future astronomical tools will vastly sharpen our ability to answer these questions. The Rubin Observatory's Legacy Survey of Space and Time will detect hundreds of interstellar objects over its planned 10-year mission, providing statistical samples large enough to test theoretical predictions about their origins, compositions, and trajectories. Space-based infrared telescopes will characterize their thermal properties and chemical compositions with unprecedented precision. These expanding data sets will either confirm that interstellar objects follow natural distributions predicted by planetary formation theory, or reveal anomalies that demand more exotic explanations. If alien probes exist among the wandering population, larger samples and better instrumentation will eventually expose their artificial nature through subtle but persistent deviations from natural behavior patterns. The philosophical implications of continued silence should not be underestimated. Each natural interstellar object we study provides another data point supporting the hypothesis that intelligence capable of interstellar engineering either does not exist, remains undetectable by our current methods, or chooses not to reveal itself through easily recognizable signatures. The accumulating evidence of cosmic loneliness grows with every confirmed natural visitor. But absence of evidence is not evidence of absence, particularly when our detection capabilities remain limited and our sample sizes remain small. The universe may yet hold surprises that challenge our current understanding of intelligence, technology, and their signatures in space. 3IATLAS, whether natural or artificial, represents one more piece of evidence in humanity's ongoing attempt to understand its place in the cosmic community. As we continue exploring increasingly speculative scenarios, the contrast between what we observe and what we imagine becomes ever more important to maintain. The real cosmos, revealed through patient observation and careful analysis, has proven strange and wonderful enough without requiring exotic additions. Whether that strange reality includes other forms of intelligence remains an open question, but one that future discoveries will ultimately answer with the clarity that only evidence can provide. Part 10. Cinematic Worst. Silent Invasion via Microseeds. Now we plunge into the realm of pure cinematic speculation, where the boundaries between plausible science fiction and observable reality blur into scenarios that would challenge everything we think we know about life, intelligence, and the cosmos. What follows represents the outermost edge of possibility. Ideas so speculative that they require suspension of multiple scientific principles while still maintaining enough connection to known physics to fuel our imagination. Picture this scenario. 3. Atlas isn't merely a probe or even a conventional spacecraft, but rather a delivery system for something far more insidious and sophisticated. Hidden within its icy matrix, microscopic devices, or perhaps even engineered biological entities, let's call them microseeds, lie dormant, awaiting activation by specific environmental triggers. These could be nanotechnological constructs designed to survive the harsh conditions of interstellar space for billions of years. Or they might represent some form of pangalactic life that spreads between star systems through exactly this mechanism. The concept is not entirely without precedent in scientific speculation. The panspermia hypothesis, while controversial and far from proven, suggests that life itself might spread throughout the galaxy via comets, asteroids, and other interstellar wanderers. Some researchers have proposed that hardy microorganisms could survive the radiation, vacuum, and extreme cold of space for millions or even billions of years, seeding new worlds when they encounter suitable conditions. But our speculative scenario goes far beyond passive panspermia. These hypothetical microseeds would represent engineered systems designed not merely to survive interstellar transit, but to remain dormant until specific activation conditions are met. Perhaps they respond to the electromagnetic signatures of technological civilizations, becoming active only when they detect radio transmissions, industrial pollutants, or other indicators of intelligence. Or maybe they're triggered by solar radiation patterns, awakening as their host object approaches stars of particular spectral types. The engineering challenges involved would be staggering beyond current comprehension. These micro-devices would need to maintain structural integrity across billion-year timescales while exposed to cosmic radiation, interstellar dust impacts, and the extreme temperature variations of deep space. They would require power sources that remain functional longer than most stars burn, information storage systems that do not degrade over geological time, and manufacturing capabilities that could bootstrap complex technology from raw materials found on alien worlds. Yet, if such technology were possible, the strategic implications would be terrifying. A single interstellar object like 3IATLAS could carry billions or trillions of microscopic seeds, each capable of establishing a foothold on any world it eventually reaches. The invasion, if we can call it that, would be silent, patient, and virtually undetectable until the activation phase began. The activation scenario in our speculative narrative might unfold centuries or millennia after 3IATLAS passes through our solar system. Perhaps the microseeds are designed to trigger when Earth's technology reaches specific thresholds, when we achieve interstellar travel ourselves, when our population reaches certain levels, or when our industrial activity produces particular atmospheric signatures. The delay would serve multiple strategic purposes, allowing time for detailed reconnaissance of human civilization, ensuring that activation occurs when humanity is sufficiently developed to serve whatever purpose the seeds are designed to fulfill, and maintaining plausible deniability about the connection between the original delivery and the eventual activation. But here's where harsh reality intrudes on this speculative fantasy. The extreme conditions that 3IATLAS has experienced during its interstellar journey would present almost insurmountable challenges to any form of complex technology or biology. Cosmic radiation alone would gradually destroy molecular structures over million-year timescales, let alone the billion-year journey suggested by the object's apparent age. Even the most radiation-resistant organisms known on Earth would succumb to such prolonged exposure. The outgassing chaos that makes 3IATLAS visible as a comet would create additional hazards for any microscopic hitchhikers. As volatile ices sublimate and expand into the vacuum of space, they would carry along dust particles and any other small-scale materials embedded in the nucleus. The violence of this process occurring every time the object approaches a star during its billion-year journey would likely destroy delicate structures and scatter any microscopic components across vast distances. The extreme dilution factors involved also argue against the practical effectiveness of such a delivery mechanism. Even if 3IATLAS contained billions of microseeds, the vast majority would be ejected into space during outgassing events, lost to the vacuum between worlds. The few that might somehow reach Earth's vicinity would face additional dilution in our planet's atmosphere and biosphere, making it virtually impossible for any meaningful concentration to accumulate in any particular location. The closest approach distance of 1.88 astronomical units provides another reality check on this speculative scenario. 3IATLAS will pass Earth at roughly twice the distance of Mars, with no possibility of direct material exchange. Any microseeds would need to survive not only the billion-year interstellar journey and the violent outgassing process, but also the subsequent journey across hundreds of millions of kilometers of interplanetary space to reach our world. Current planetary protection protocols developed by space agencies to prevent contamination of both Earth and other worlds provide frameworks for how we might respond to hypothetical material capture from objects like 3IATLAS. These procedures involve strict containment protocols, analysis in specialized biosafety laboratories, and careful evaluation of any biological or technological signatures. But such protocols assume direct sample return missions, not the passive capture of microscopic materials ejected across vast distances. The monitoring challenges for detecting such a speculative threat would be enormous. How do you search for microscopic devices or organisms that might be designed to remain dormant for centuries? What signatures would they produce that could be distinguished from natural microorganisms, space dust, or terrestrial contamination? The task would be like searching for needles in a haystack the size of our entire solar system. Long baseline radar systems, the kind used to track space debris and potentially hazardous asteroids, would be unlikely to detect objects as small as microscopic seeds. Optical surveys fare even worse when dealing with particles measured in micrometers rather than kilometers. Even if such monitoring were theoretically possible, the resource requirements would be staggering, demanding constant vigilance across the entire volume of space around Earth. This brings us to the central weakness of our speculative silent invasion scenario. It violates fundamental principles of engineering efficiency. Any civilization capable of designing billion-year interstellar delivery systems would presumably have access to far more direct and reliable methods of achieving whatever goals such an invasion might serve. The complexity, uncertainty, and time delays involved in microscopic seed distribution make it an implausibly inefficient approach compared to alternatives like directed energy transmission, conventional spacecraft, or even simple radio communication. The scenario does serve one valuable purpose in our speculative exploration. It illustrates how our imaginations can run ahead of physical possibility when we're confronted with cosmic mysteries. The same sense of wonder and cosmic anxiety that drives legitimate scientific inquiry can also generate fears that exceed the bounds of plausible reality. Distinguishing between reasonable caution and unfounded speculation becomes crucial when dealing with genuinely unprecedented phenomena. Our documentary treatment of such scenarios requires clear and prominent disclaimers about their speculative nature. Viewers need to understand that we're exploring the landscape of imagination rather than the territory of established fact. These thought experiments can be valuable for expanding our thinking about possibilities, but they shouldn't be mistaken for probable or even plausible realities. The counter-narrative remains straightforward and compelling. The simplest explanation for 3IATLAS's behavior is that comet dust behaves exactly like comet dust. The object displays all the characteristics we expect from natural cometary material: appropriate spectroscopic signatures, predictable thermal behavior, and outgassing patterns that correlate precisely with solar heating. No additional hypotheses are required to explain its observed properties. As we near the end of our speculative journey into increasingly dramatic scenarios, it's worth reflecting on what these thought experiments reveal about human psychology and our relationship with cosmic uncertainty. Our tendency to imagine exotic explanations for unusual phenomena reflects both our creativity and our anxiety about our place in a universe that often seems indifferent to our existence. The real 3IATLAS, the observed, measured, and analyzed object racing through our solar system at incredible speed, remains remarkable enough without requiring exotic additions to its story. It's an ancient wanderer from another stellar system, carrying chemical signatures of alien environments, offering us a brief window into the deep history and vast scale of our galaxy. That's extraordinary enough to fuel wonder and scientific investigation without needing to invoke invasion scenarios or hidden technologies. But the exercise of exploring such possibilities serves its own purpose in our ongoing attempt to understand our cosmic context. By pushing speculation to its limits, we better appreciate both the genuine mysteries that surround us and the constraints that physics and evidence place on reasonable explanation. The universe has proven strange enough through natural processes alone, perhaps stranger than our imaginations can readily encompass, but strange in ways that ultimately yield to patient observation and careful analysis. Part 11. If 3IATLAS were a visitor, how would we respond? The response so far has been a testament to the best aspects of human scientific collaboration. a choreographed dance of telescopes, institutions, and individual researchers working together to extract maximum knowledge from a fleeting opportunity. Within hours of the initial discovery by the ATLAS survey on July 1, 2025, a global network of observatories had swung into coordinated action, demonstrating how modern astronomy operates as a truly international enterprise. The immediate response followed protocols developed over decades of asteroid and comet discovery. The Minor Planet Center at Harvard-Smithsonian Astrophysical Observatory served as the central clearinghouse for astrometric observations, collecting position measurements from observatories worldwide and refining the object's orbital elements with each new data point. The European Space Agency's Space Situational Awareness Program added its own tracking capabilities, while NASA's Planetary Defense Coordination Office evaluated any potential Earth impact risk, a calculation that quickly ruled out any collision threat. But 3IATLAS's interstellar nature elevated the response beyond routine asteroid tracking procedures. The Hubble Space Telescope received priority target of opportunity scheduling, interrupting previously planned observations to image this unprecedented visitor. The James Webb Space Telescope followed suit, dedicating precious observing time to spectroscopic analysis of the object's unusual carbon dioxide-dominated coma. Ground-based observatories from Chile's Atacama Desert to Hawaii's Mauna Kea contributed complementary observations across the electromagnetic spectrum. This coordinated response illustrates how the astronomical community has evolved to handle rapid response scenarios. Unlike the early days of astronomy, when discoveries might remain hidden in individual researchers' notebooks for months or even years, modern astronomical surveys automatically share their findings through established networks. The Central Bureau for Astronomical Telegrams of the International Astronomical Union, despite its antiquated name, provides nearly instantaneous notification of significant discoveries to researchers worldwide. The information flow surrounding 3IATLAS has been remarkably transparent. NASA's official website provides regular updates on observational results, complete with detailed technical information and accessible explanations for the general public. The European Space Agency has published similar updates, emphasizing the collaborative nature of the observation campaign. Popular astronomy publications like Sky and Telescope have offered both detailed technical coverage and practical observing guides for amateur astronomers eager to glimpse this interstellar visitor through their own telescopes. But imagine if the speculative scenarios considered earlier in this investigation proved accurate. Suppose future observations began to reveal signatures that could not be explained by natural processes, coherent radio transmissions, controlled trajectory adjustments, or the deployment of secondary objects throughout our solar system. How would our institutions and procedures scale up to handle what might become the most significant discovery in human history? The existing framework provides some guidance. The International Astronomical Union has protocols for verifying extraordinary claims, requiring independent confirmation from multiple observatories before accepting results that challenge established scientific understanding. The SETI Institute has developed communication protocols for potential first contact scenarios, including guidelines for information sharing, public notification, and international cooperation. Space agencies maintain planetary protection procedures designed to prevent contamination of Earth by alien microorganisms or more exotic forms of life. Yet none of these frameworks were designed to handle the discovery of active alien technology operating within our solar system. The scale of coordination required would dwarf anything previously attempted in scientific research. Questions of jurisdiction would immediately arise. Which international body has authority over first contact protocols? How do you coordinate response among nations that may view such a discovery as either an opportunity or a threat? What happens when scientific curiosity collides with security concerns? The political dimensions would be staggering. Any confirmation of alien technology would instantly become a matter of national security for every major power on Earth. Military establishments, which currently view space primarily as a domain for surveillance and communication, would suddenly confront the reality of non-human intelligence with potentially superior technological capabilities. The balance between transparency and security, usually tilted toward openness in astronomy, could shift dramatically toward classification and restricted access. The technical challenges would be no less daunting. Present-day spacecraft require years to reach the outer solar system, where 3I-ATLAS now resides, and decades to achieve interstellar speeds. If the object were artificial and time-sensitive communication were required, our only practical option might be radio transmission. Assuming the alien technology used recognizable or decodable communication protocols, the lack of any realistic interception capability highlights humanity's current technological limitations. Despite decades of progress in robotic exploration, we remain confined to our immediate solar neighborhood, with transit times measured in years rather than months. Any meaningful interaction with a fast-moving interstellar object would require spacefaring capabilities we do not currently possess and cannot develop quickly enough for 3I-ATLAS. Public communication strategies would face unprecedented challenges. How do you announce the discovery of alien intelligence without triggering panic or societal disruption? The careful, measured tone that space agencies have used in 3I-ATLAS announcements, emphasizing scientific curiosity while downplaying sensational interpretations, would need to evolve rapidly to handle far more extraordinary claims while maintaining credibility and public trust. The lessons of past false alarms would become crucial. The WOW signal detected by SETI researchers in 1977 generated enormous excitement but could not be confirmed. The unusual properties of Oumuamua in 2017 also prompted speculation about artificial origin before more conventional explanations prevailed. Scientists and communicators have learned the importance of distinguishing between intriguing observations and definitive conclusions. Media management would be critical if alien technology were confirmed. The 24-hour news cycle's hunger for spectacle could overwhelm cautious analysis with speculation and misinformation. Social media platforms, too, would face great difficulty distinguishing verified updates from a flood of conspiracy theories, hoaxes, and distortions. The economic impact alone would justify meticulous planning. Financial markets would likely experience severe volatility as investors attempted to account for the implications of alien technology. Entire industries could face existential questions if alien science offered radical alternatives to energy, transportation, or manufacturing. Global economic stability might depend on institutions' ability to manage the transition from speculation to confirmed reality. Educational institutions would feel immediate pressure to revise curricula, research priorities, and core assumptions about humanity's place in the universe. The philosophical impact would ripple through all academic disciplines, from astronomy and physics to anthropology, theology, and political science. Universities that spent centuries studying terrestrial phenomena would suddenly need to confront the reality of non-human intelligence. The time constraints imposed by the rapid trajectory of 3I-ATLAS add further urgency. Unlike predictable astronomical phenomena, interstellar visitors arrive and depart on timescales dictated by physics, not human convenience. Any meaningful response would need to be devised and enacted in months, not years. Yet the actual response to 3I-ATLAS has shown remarkable efficiency. The global astronomical community identified the object, confirmed its interstellar origin, coordinated multi-wavelength observations, and initiated detailed analysis within weeks. This record suggests that existing institutions, while imperfect, offer a solid foundation for unprecedented discoveries. Protocols for handling confirmed alien contact have been debated for decades by SETI researchers, astrobiologists, and legal scholars. While no preparation can cover every contingency, they provide a starting point for rapid decision-making under extraordinary circumstances. Perhaps most importantly, the response to 3I-ATLAS has emphasized curiosity over fear, investigation over panic, and international cooperation over secrecy. These values, embodied in transparent data sharing and collaborative research, represent humanity's best approach to cosmic mysteries regardless of their ultimate explanation. The real-world response demonstrates that we already possess the technical and institutional frameworks required to study unprecedented phenomena effectively. Whether those same frameworks would be enough for actual first contact remains an open question. Still, the coordinated professional response to 3I-ATLAS offers reason for optimism about humanity's ability to face extraordinary encounters. as speculation about alien contact gives way to grounded discussion on perspective and scientific method. The investigation of 3IATLAS stands as a case study in how modern civilization confronts the unknown. The combination of technical capability, institutional coordination, and intellectual curiosity that has defined this investigation serves as a template for engaging with mysteries that may ultimately prove even more transformative to our sense of place in the universe. Part 12. Containment or curiosity. The question of how we balance scientific curiosity against hypothetical risks reflects one of humanity's oldest dilemmas. The same impulse that drove us across oceans, up mountains, and out into space despite ever-present dangers. In the case of 3IATLAS, the balance tilts decisively toward curiosity, and for good reason. Its trajectory and properties eliminate most containment scenarios while maximizing opportunities for discovery. The doctrine of planetary protection, shaped over decades of exploration, provides frameworks for managing risks in both directions, protecting Earth from alien microorganisms while also protecting other worlds from contamination by terrestrial life. But those protocols were designed for sample return missions or close spacecraft encounters, not for distant interstellar objects exhibiting no evidence of biology. The core of planetary protection is proportional response. That is why NASA's Perseverance Mars rover mission included extraordinary precautions for possible sample return, and why spacecraft heading for Europa undergo strict sterilization to avoid forward contamination of potentially habitable environments. 3IATLAS presents a different case entirely. Its minimum approach, 1.8 astronomical units, about 270 million kilometers, makes material transfer impossible. No interception mission is planned or even feasible given its extreme speed. Thus, containment becomes largely theoretical. This very distance has enabled a notably open atmosphere of research. Images from Hubble, spectra from James Webb, and ground-based observations have all been deposited into standard archives, available worldwide for analysis. This transparency exemplifies the scientific method at its best. Multiple investigators working independently on the same evidence, reaching consistent conclusions. The open archive culture fostered by observatories like the Mikulski Archive for Space Telescopes, making Hubble and Webb data freely accessible, has democratized astronomy in ways unimaginable just decades ago. The European Southern Observatory hosts its own archives for ground data, while amateurs upload images and light curves through citizen science platforms. This openness contrasts sharply with the secrecy we might expect from military or intelligence agencies facing the possibility of alien contact. The scientific community's preference for transparency reflects both the requirements of peer review and the philosophical commitment to universal knowledge. The 3IATLAS investigation shows how these principles apply even when the object in question might, in principle, represent our first brush with alien intelligence. The information ecosystem surrounding this comet illustrates both the benefits and pitfalls of global real-time communication. Scientific results now circulate within hours, enabling collaboration across continents. Yet the same networks carry misinformation, conspiracy theories, and sensationalism capable of distorting public understanding. Social media algorithms reward engagement, amplifying bold claims at the expense of rigor. For rational public discourse, distinguishing between legitimate scientific uncertainty and baseless speculation is paramount. 3IATLAS provides a case study. Reputable sources consistently stress its unusual features yet natural origin, acknowledging uncertainty but avoiding reckless claims. Less credible outlets exaggerate preliminary findings or frame speculation as fact, fueling rumors of government cover-ups. Visuals matter as well. Processed and enhanced images from Hubble and Webb, intended for scientific analysis, can strike the public as astonishing and otherworldly. The challenge lies in presenting these images in contexts that emphasize their scientific rather than sensational importance, showing how the observed features confirm cometary behavior rather than implying alien technology. The question of containment versus curiosity takes on different dimensions when we consider not physical containment, but information containment. Should certain types of astronomical discoveries be classified or restricted in dissemination? The scientific community has generally answered no, arguing that the benefits of open collaboration outweigh hypothetical security risks from publicly available astronomical data. This position reflects both practical and philosophical considerations. Practically, astronomy operates most effectively as a global enterprise where researchers share data, verify results, and build upon collective knowledge. Philosophically, the view from space has historically united humanity rather than divided it, underscoring our common cosmic heritage rather than terrestrial conflicts. The precedent set by previous, potentially anomalous astronomical discoveries supports continued openness. The pulsar discoveries of the 1960s, briefly labeled LGM for Little Green Men, ultimately revealed new physics, not extraterrestrial intelligence. The WOW signal detected by SETI researchers remains unexplained, but it has been thoroughly documented and analyzed publicly. Even the unusual properties of Oumuamua were studied through transparent international collaboration rather than secrecy. Citizen science contributions to observations of 3IATLAS demonstrate another facet of the curiosity over containment approach. Amateur astronomers with modest equipment captured images and light curves that complemented professional observations, adding to the database that will ultimately enrich scientific understanding. Such democratization of research would be impossible under restrictive containment policies, but has proven invaluable for genuine advancement. The potential role of the SPHEREX mission in mapping Atlas's extended carbon dioxide coma illustrates how next-generation surveys will expand our to study such objects. Wide-field infrared missions like SPHEREX can complement the detailed spectroscopy of the James Webb Space Telescope, creating comprehensive portraits of interstellar visitors no single instrument could provide alone. Looking forward, the Vera Rubin Observatory's Legacy Survey of Space and Time promises to revolutionize our knowledge by detecting hundreds of interstellar visitors during its planned operational lifetime. This statistical approach will either confirm that objects like Atlas are natural phenomena following predictable distributions or reveal anomalies requiring more exotic explanations. The institutional approach to studying future discoveries has been shaped by the Atlas experience. Rapid coordination between observatories, transparent data sharing protocols, and emphasis on international cooperation provide a template for addressing even more unusual findings. Should genuinely anomalous objects be detected, it appears the scientific community is well prepared to study them through the same open and collaborative methods that defined the 3IATLAS investigation. The balance between skepticism and openness that characterized professional responses to Atlas provides a further model for future discoveries. Healthy science demands extraordinary evidence for extraordinary claims, but also requires staying open to possibilities that push the limits of current understanding. The Atlas investigation has shown how to maintain this balance, acknowledging unusual characteristics while avoiding unfounded speculation. Risk assessment for future interstellar objects will benefit directly from this precedent. Atlas's safe passage through the solar system, its consistent behavior as a natural comet, and the absence of anomalous signatures establish baseline expectations for similar visits. Future objects that significantly deviate from this behavior may require different treatment, but the default assumption will likely hold that natural explanations must always be tested exhaustively before entertaining exotic possibilities. The educational value of the Atlas investigation extends well beyond its immediate discoveries, showing how modern astronomy operates as a transparent, collaborative, evidence-based enterprise. The project demonstrated how institutions coordinate responses to groundbreaking events, how data sharing expedites progress, and how scientific skepticism shields against both premature conclusions and reflexive dismissal of unusual phenomena. As we move toward broader questions of cosmic perspective and humanity's place in the universe, the Atlas investigation serves as a case study of how our species approaches the unknown. The emphasis on curiosity over fear, collaboration over competition, and evidence over speculation offers reason for optimism about our ability to confront even more profound discoveries in the years and decades ahead. Part 13. scale of the cosmos, and our signals. The journey that brought Atlas to our cosmic doorstep spans distances and timescales that defy human comprehension. Yet understanding these scales is essential for grasping both the object's significance and our own place in the vast theater of galactic evolution. When we speak of thick disk galactic origins, we refer to a story that began when the universe was less than half its present age, when stellar populations differed greatly from those we see today, and when the Milky Way was still a turbulent stellar nursery. The thick disk represents an older generation of stars formed roughly 10 to 12 billion years ago in the galaxy's chaotic youth. Unlike the thin disk where our Sun resides, a relatively orderly region where stars follow nearly circular orbits, the thick disk contains stars with eccentric, tilted paths reflecting their violent birth conditions. If 3IATLAS indeed comes from this ancient population, its nucleus carries a record of stellar environments that existed long before our solar system was even conceived in a cloud of interstellar gas. The scales of this journey become almost poetic when visualized. Atlas may have wandered the galaxy for billions of years, while countless generations of stars were born, lived, and died. Massive stars that existed when this object began its interstellar odyssey exploded long ago as supernovae, scattering heavy elements and igniting new cycles of star formation. Planetary systems have formed, evolved, and perhaps nurtured life innumerable times. During this wanderer's trek through the cosmic dark, travel times dwarf any human concept of duration. If Atlas has indeed traveled for 5 billion years, a conservative estimate based on its thick disk origin, then it has journeyed more than 1,000 times longer than complex life has existed on Earth. During that span, our planet experienced the Cambrian explosion, 5 great mass extinctions, the reign and demise of the dinosaurs, and the eventual rise of human civilization. Yet, from the perspective of this cosmic traveler, all of human history is but the last microsecond of its multi-billion-year voyage. The distances are equally staggering. Even at Atlas's tremendous velocity of over 130,000 miles per hour, crossing substantial portions of the galaxy requires millions of years. Along the way, it may have encountered hundreds or thousands of stellar systems, passing close enough to feel their gravity, perhaps even witnessing the birth of planets around stars now in their ancient decline. Each gravitational interaction, silent and unseen, adjusted its trajectory slightly, a cosmic game of pinball played on galactic scales. The combined effect of millions of such encounters could account for Atlas's present extraordinary speed, each stellar brush nudging it onward. Its chemical diversity gains new meaning when viewed against this backdrop. Its carbon dioxide-rich composition may reflect formation around a very different kind of star than our Sun, in neighborhoods where fusion processes or interstellar chemistry were unlike those we know. Here, Atlas serves as a physical sample of alien chemistry, carrying molecular records from stellar regions we may never observe firsthand. This chemical archaeology extends our knowledge of galactic history in ways starlight alone cannot provide. While distant stars can be studied through spectroscopy to infer their properties, interstellar objects such as Atlas carry real matter, isotopes, minerals, volatile compounds, that formed around stars billions of years ago. They are fragments of alien worlds delivered to our doorstep. Our own radio bubble, the expanding sphere of human electromagnetic radiation, offers humbling perspective on these scales. Since Marconi's first wireless transmissions in the late 19th century, our signals have spread light speed outward, now reaching stars within only about 120 light-years. This seems vast until we recall that the Milky Way spans about 100,000 light-years. Our presence is a tiny bubble in the galactic ocean. That bubble contains only a few thousand systems among an estimated 400 billion stars. Even our most powerful transmissions, designed for planetary distances, would reach nearby stars merely as faint whispers. Thus, the idea that 3IATLAS could have been drawn here by our electromagnetic footprint collapses against these realities. Its age and our minuscule reach make the suggestion implausible. The pervasive silence encountered when searching for extraterrestrial radio signals, the great silence, at the core of the Fermi paradox, becomes far less surprising. Even if the galaxy hosts thousands of transmitting civilizations, their signals would be vanishingly faint across these distances. The inverse square law dictates that doubling the distance quarters the apparent intensity, making detectable communication arduous even with technologies far beyond ours. Broadcasting with enough power to be obvious across interstellar space would require outputs rivaling stars themselves. This may explain why SETI's decades of scanning vast frequency ranges have yielded no confirmed artificial signals. The same energy realities apply to interstellar travel. Accelerating even a small probe to high interstellar speeds would demand energy equivalent to the yearly output of entire industrial nations. Larger craft would need more still, exceeding even planetary-scale capacities. Atlas's achievement of extreme velocity through countless gravitational interactions shows how the galaxy itself functions as a natural accelerator, patiently lending energy to wandering bodies. This plausible mechanism explains Atlas's speed without invoking alien propulsion. Statistical reasoning reinforces this. If planetary formation regularly ejects rocky and icy fragments, as simulations suggest, the galaxy should contain trillions of wanderers like Atlas. The Rubin Observatory's projected few detections per year represent only the tiniest fraction of that sprawling population, limited by technology and observational reach. The chemical and physical diversity we have seen so far may barely hint at the true range among these countless travelers. Future surveys may uncover even more exotic specimens than Atlas, broadening our grasp of the processes shaping distant starscapes. Temporal scales deepen this context. Over billions of years, successive generations of stars created heavier elements, enriching the galaxy. Objects born early in this history, like Atlas, would bear the imprint of a young, metal-poor galaxy very different from what we see today. The natural comet hypothesis has the advantage of consistency with known physics, established cometary behavior, and the observed properties of previous interstellar visitors. Overturning that consensus would require evidence that clearly demonstrates the inadequacy of natural explanations and positively supports artificial alternatives. The intellectual exercise of considering these possibilities should not distract from the remarkable reality of what 3IATLAS actually represents. Even as a natural comet, this ancient wanderer carries information about stellar environments we've never visited, chemical processes that occurred billions of years ago, and the deep history of our galactic neighborhood. That is extraordinary enough without requiring exotic explanations. As we continue this speculative journey, it is worth remembering that the most profound discoveries in astronomy have often come from careful observation of apparently ordinary objects. Pulsars, quasars, gamma-ray bursts, and gravitational waves all began as mysterious signals that eventually revealed new physics. Whether 3IATLAS ultimately proves to be a conventional comet or something more unusual, it has already expanded our understanding of interstellar space and the diversity of objects that wander between the stars. The next phase of our speculative exploration will venture into even more dramatic scenarios, not because they are likely, but because they illustrate the kinds of questions that arise when we encounter something unprecedented in our cosmic experience. These thought experiments will push the boundaries of possibility while maintaining clear distinctions between speculation and established fact, between what we imagine and what we actually know. Part 6. Worst-case speculative scenario. A dark forest trigger. We now venture into the deepest realm of speculative territory, where the shadows of cosmic possibility stretch towards scenarios that would fundamentally alter our understanding of our place in the universe. What follows is pure thought experiment, a mental journey into implications and possibilities that current evidence does not support, but which illustrate the profound questions that could emerge if our assumptions about 3IATLAS prove inadequate. The dark forest hypothesis emerges from both science fiction and serious SETI discourse. Drawing its name from Liu Cixin's acclaimed novel, but representing a genuine philosophical position about the nature of cosmic civilization. The idea suggests that advanced civilizations might remain deliberately hidden from one another, operating under the assumption that revealing one's existence and capabilities could invite predation from even more advanced neighbors. In such a universe, silence becomes a survival strategy, and any civilization that broadcasts its presence risks annihilation from threats it cannot perceive or comprehend. If we allow ourselves to imagine, and we stress this is pure imagination, that 3IATLAS represents not a natural comet, but some form of reconnaissance probe, the implications would be staggering. Such a scenario would suggest that our solar system is being surveyed by intelligences capable of engineering objects that can survive billion-year journeys between stars while remaining virtually indistinguishable from natural phenomena. The very perfection of its disguise would indicate a level of technological sophistication that dwarfs our current capabilities. Consider the engineering requirements such a scenario would demand. A probe designed to pass for a comet would need to mimic every aspect of natural cometary behavior. The correct spectroscopic signatures, appropriate outgassing patterns that respond realistically to solar heating, surface properties that reflect light in ways consistent with natural ices and rock. It would need to carry sufficient volatile materials to maintain its disguise throughout its passage through our solar system, while simultaneously housing whatever sensors, processors, and communication systems would justify such an elaborate mission. The power requirements alone would be formidable. Maintaining active systems across interstellar distances and billion-year timescales would demand energy sources far beyond our current technology. Perhaps some form of radioisotope thermoelectric generator could provide power for millennia. Or maybe advanced fusion reactors could operate on trace interstellar hydrogen. The probe might even harvest energy from cosmic rays or magnetic field interactions during its journey through space. But let's push this speculative scenario to its dramatic conclusion. Imagine that our continued observation of 3IATLAS begins to reveal anomalies that cannot be explained by natural processes. Perhaps radio telescopes detect brief structured transmissions as the object passes through the outer solar system. Maybe its trajectory shows minute but unmistakable course corrections that suggest active guidance. Or possibly its chemical emissions display patterns too complex and organized to result from random sublimation. The trigger moment in this speculative narrative might arrive when 3IATLAS begins to deploy secondary objects, smaller probes that separate from the main body and take up positions throughout our solar system. One might establish orbit around Venus, another around Mars, others scattered through the asteroid belt or positioned at gravitationally stable Lagrange points. Suddenly, our solar system would host a surveillance network of unknown origin and capability. The question that would immediately arise: how should humanity respond? This hypothetical scenario would instantly become the greatest diplomatic and strategic challenge our species has ever faced. Unlike the gradual first contact scenarios often depicted in science fiction, the discovery of an active surveillance network would confront us with the reality of technologically superior intelligence already operating in our immediate cosmic neighborhood. The governance questions would be unprecedented and urgent. Who has the authority to speak for Earth? The United Nations, the major space agencies, individual nations with advanced space capabilities, the scientific community that made the discovery. The complexity of achieving global consensus on something so momentous staggers the imagination, particularly given our species' track record of cooperation on far simpler challenges. The active SETI debate would suddenly shift from theoretical discussion to immediate practical concern. The SETI community has long debated the wisdom of transmitting signals into space versus merely listening for signals from other civilizations. Some argue that advertising our presence could attract unwanted attention from potentially hostile aliens. Others contend that remaining silent while conducting increasingly sophisticated astronomical observations provides no real protection. Any civilization capable of interstellar travel would likely detect our technological signatures regardless of our transmission policies. But in our speculative scenario, the choice might be taken from us. If 3IATLAS and its hypothetical secondary probes were actively studying human civilization, our response itself would become part of the data being collected. Silence might be interpreted as wisdom or fear. Attempts at communication might suggest aggression or curiosity. Even the internal debates about how to respond would reveal fundamental aspects of human nature and social organization to whatever intelligence was monitoring us. The crisis communication challenges would be extraordinary. How do you inform the global public about the presence of alien surveillance systems without triggering panic? How do you maintain scientific objectivity while acknowledging possibilities that exceed our current understanding? How do you distinguish between verified observations and speculative interpretations when the stakes could involve the future of human civilization? The scenario would likely unfold through a series of expert roundtables, emergency sessions of scientific organizations, and carefully crafted public briefings. Governments would need to balance transparency with stability, providing enough information to maintain credibility while avoiding the social disruption that might result from confirming humanity's first contact with non-human intelligence. Misinformation would become a critical concern. The mere suggestion of alien surveillance would spawn countless conspiracy theories, false flag accusations, and claims of government cover-ups. Distinguishing between legitimate scientific observations and baseless speculation would become crucial for maintaining rational public discourse about the most important discovery in human history. The technological implications would be equally profound. If 3IATLAS revealed capabilities that exceeded our current physics, it might provide insights into propulsion systems, energy generation, material science, or communication methods that could revolutionize human technology. The scientific windfall could accelerate our development by centuries, assuming the intelligence behind the probe allowed us to continue existing and developing. But perhaps the most unsettling aspect of this speculative scenario would be the temporal implications. If 3IATLAS had been traveling for billions of years, it might represent technology from a civilization that achieved interstellar capability when our galaxy was radically different from its current state. The intelligence that launched it might no longer exist, leaving behind only automated systems carrying out missions designed by minds that died out before our sun was born. This raises the chilling possibility that we might be dealing not with active alien intervention, but with the ghost of some ancient civilization, autonomous systems following programmed directives across deep time, perhaps no longer serving any living intelligence, but continuing to execute their original mission parameters with mechanical precision. Of course, and this bears constant repetition, none of this speculative narrative is supported by current observations of 3IATLAS. Every measurement, every spectrum, every image continues to support the natural comet hypothesis. The object behaves exactly as astronomical theory predicts an interstellar comet should behave. Its chemical signatures, while unusual, fall within the range of natural processes. Its trajectory follows the laws of physics, without requiring exotic explanations. The value of this speculative exercise lies not in its probability, but in its illustration of how quickly our cosmic perspective could change if our assumptions proved inadequate. It reminds us that the universe has surprised us before and will likely surprise us again. And it highlights the importance of maintaining both healthy skepticism about extraordinary claims and openness to possibilities that exceed our current understanding. But as we continue this journey through increasingly speculative territory, remember that we're exploring the landscape of possibility rather than the terrain of established fact. The real 3IATLAS remains a fascinating natural phenomenon, ancient, fast, chemically unusual, but fundamentally comprehensible within our current scientific framework. Whether that understanding will prove sufficient remains an open question, but one that future observations will ultimately answer with the cold clarity that only evidence can provide. Part 8. Great Filter Alarms. The concept of the Great Filter emerges from one of the most profound questions facing any technological civilization. If the universe should be teeming with intelligent life, why do we see no evidence of it? This philosophical puzzle, first articulated by physicist Enrico Fermi in the 1950s, has spawned decades of speculation about barriers that might prevent life from arising, evolving, or surviving long enough to spread throughout the galaxy. In our speculative exploration of 3IATLAS, we must confront the possibility that this ancient wanderer might carry messages from intelligences that encountered their own insurmountable barriers. The Great Filter hypothesis suggests that somewhere in the long chain of evolutionary development, from simple chemistry to spacefaring civilization, there exists a step so improbable, so difficult, or so dangerous that virtually all attempts to pass through it result in failure. This filter could occur early in the process, perhaps in the transition from non-living matter to self-replicating systems. Or it might emerge later when civilizations develop technologies powerful enough to destroy themselves faster than they can learn to use them wisely. If we permit ourselves to imagine that 3-ATLAS represents engineered technology rather than natural phenomena, we must immediately confront the question of its maker's fate. The object's apparent age, potentially billions of years, places its origin in the deep history of our galaxy, when stellar populations, chemical abundances, and cosmic conditions differed substantially from those we observe today. If this ancient visitor were indeed artificial, did the civilization that created it survive long enough to see it reach our solar system? The timescales involved are almost incomprehensible. Human civilization, from the first agricultural settlements to our current space age, spans roughly 10,000 years. Recorded history covers perhaps 5,000 years. Our technological civilization has existed for mere centuries. Yet 3-ATLAS, if artificial, would represent technology that has been operational for millions of times longer than our entire civilizational history. This raises profound questions about technological longevity versus biological survival. Perhaps the most haunting possibility is that we might be encountering probes that persist long after their makers have vanished. Cosmic messages in bottles floating through the galaxy, carrying information from civilizations that solved the technical challenges of interstellar communication, but ultimately succumbed to other forms of the Great Filter. Consider the engineering implications of creating technology that remains functional across such timescales. Our most durable human artifacts, the pyramids, ancient stone monuments, certain radioactive isotopes, operate on timescales of thousands to millions of years. But maintaining complex electronic systems, propulsion mechanisms, and artificial intelligence across billions of years would require engineering principles we can barely imagine. While our terrestrial world churns with uncertainty, 3IATLAS follows laws that have governed motion in space since the universe began. Its departure is scheduled not by human decision, but by the fundamental forces that shape reality itself. In an age of manufactured anxiety and artificial urgency, such cosmic dependability offers a profound kind of comfort. The answer to our investigation's central question, what's the worst-case scenario, has proven refreshingly mundane. No Hollywood catastrophe awaits. No alien invasion threatens our civilization. No cosmic disruption will alter Earth's orbit or climate. The worst case, in terms of actual physical threat, is quite literally nothing at all. 3-ATLAS will leave our solar system exactly as it arrived, silently, safely, and in accord with the precise predictions of mathematical physics. But perhaps calling this outcome mundane misses its real significance. The fact that we can predict the behavior of an object that has traveled for possibly billions of years, that was forged around a star we have never seen, and that carries chemical signatures from environments we've never studied directly. This predictability represents one of science's greatest triumphs. The laws of physics operate with such consistency that phenomena separated by cosmic distances and geological time still follow the same fundamental rules. The strangeness that 3-ATLAS has revealed proves no less fascinating for being natural. Its chemistry, unusually rich in carbon dioxide, challenges our assumptions about typical comet compositions, expanding our understanding of the diversity of materials that can form around different kinds of stars. Its apparent origin in the thick disk of the galaxy suggests formation in stellar environments very different from our local neighborhood, offering a sample of ancient galactic chemistry that we can study in exquisite detail. These unusual properties have already influenced how astronomers think about planetary formation, cometary evolution, and the chemical diversity of interstellar objects. Papers published on 3-ATLAS will be cited for decades as scientists incorporate its lessons into broader theories of how icy bodies form and evolve throughout the galaxy. Its scientific impact extends far beyond a single comet, illuminating processes that operate around countless distant stars. The speculation we've engaged in throughout, scenarios of alien technology, ancient civilizations, or exotic physics, served its role by exercising our imagination and highlighting the questions that arise when we encounter genuine cosmic mysteries. But the evidence consistently points toward natural explanations which, though remarkable, stay within the boundaries of known physical law. Such an outcome should not disappoint us. The universe has already proven strange and wondrous enough through natural processes alone, from quantum mechanics to black holes to the accelerating expansion of the cosmos. Adding artificial intelligence or exotic technology to this already extraordinary reality may not be necessary for inspiring the awe and cosmic perspective that propels scientific inquiry. The music that might accompany our farewell to 3IATLAS should be neither ominous nor triumphant, but contemplative, something that captures both the mystery and comprehensibility of cosmic phenomena. Perhaps Holst's The Planets or Barber's Adagio for Strings, compositions that evoke the vastness of space while holding emotional resonance. The tone should invite reflection, not thrill, wonder, not fear. Throughout this investigation, we have worked to maintain a clear boundary between established science and imaginative speculation. Where data ended and conjecture began has been made explicit, allowing audiences to distinguish what we actually know from what we only imagine. That transparency reflects not just intellectual honesty, but also necessity in an age when misinformation moves faster than fact-checking. The final message that emerges is not about impacts or invasions, but about a subtler danger: cosmic anxiety, the fear that rises when we meet phenomena beyond our immediate understanding. 3IATLAS has shown that such fears can be dissolved by patient observation, careful analysis, and international collaboration among those committed to evidence. The epilogue cards that might close our documentary should guide interested viewers to the wealth of publicly available information that made this investigation possible. NASA's official pages on 3IATLAS provide authoritative summaries of results. The Space Telescope Science Institute archives preserve the actual Hubble and Webb images and spectra that feed our knowledge. Professional journals and popular astronomy magazines supply technical analysis alongside accessible summaries for the public. These resources are more than bibliographic references. They embody the democratic spirit that has characterized the 3IATLAS inquiry since its first days. The choice to make observational data publicly available through standard astronomical archives reflects a philosophical commitment to shared knowledge that transcends borders and institutions. Such openness is a hopeful model of how humanity might face even greater discoveries that may lie ahead. The promise of future interstellar visitors adds anticipation to our farewell. The Rubin Observatory will detect dozens of similar objects in the coming decade, each offering insights into galactic chemistry, planetary formation, and the population of cosmic wanderers. Some may prove even more chemically exotic than 3IATLAS. Others may display properties that challenge our understanding in completely new ways. Each new discovery will expand the database of interstellar characteristics, enabling statistical studies impossible with our sample today. Their population traits, chemical diversities, and dynamical behaviors will refine theories of galactic evolution and planetary formation on scales far beyond our solar backyard. The credits that acknowledge the observatories, archives, and individual researchers behind the 3IATLAS investigation serve a deeper purpose than attribution. They remind us that great discoveries arise not from isolated genius, but from networks of collaboration, not from singular inspiration, but from the scaffolding of institutional support. The coordination across ground-based surveys, space telescopes, and archival repositories that enabled such rapid characterization of this interstellar visitor represents astronomy at its most effective. And now, 3IATLAS fades into the cosmic distance, carried by momentum earned in a billion-year journey through interstellar space. It leaves behind not only scientific data and papers, but also a case study, a testament to how human civilization meets the unknown with instruments instead of weapons, with curiosity instead of fear, with collaboration instead of rivalry. These choices reflect our highest aspirations for engaging with cosmic mysteries that may be even more profound than this ancient wanderer from between the stars. The silence that follows 3IATLAS's departure will not be empty, but anticipatory, waiting for the next cosmic messenger that will surely come, carrying its own chemical signatures from distant stellar neighborhoods, its own challenges to our understanding, and its own opportunities to expand humanity's knowledge of the universe that gave us birth. In that waiting, in that continued watching of the skies, lies perhaps the most hopeful aspect of our relationship with the cosmos. The conviction that there will always be new wonders to find, new questions to ask, new reasons to gaze upward with. Curiosity rather than fear. The gentle fade to black that could conclude our visual story follows. 3IATLAS, as it disappears into the stellar backdrop. No longer a distinct traveler, but part of the cosmic fabric from which it briefly emerged. Its passage through our solar system spanned only a few months of a journey that has lasted geological ages and will continue for many more. We were privileged to witness this fleeting cosmic moment, to study this ancient traveler, and to add its story to the growing catalog of wonders that fill the space between stars. Good night, cosmic messenger. Thank you for the lessons, the data, and the reminder that the universe remains far stranger and more wondrous than our earthbound imaginations suggest. Safe travels on your continuing journey through the galaxy, carrying the chemical secrets and ancient memories locked in your nucleus, testimony to stellar environments and conditions of formation that existed long before our world ever knew the warmth of its own star. Until we meet your cousins from other distant systems, other ancient epochs, other corners of the cosmic wilderness that surrounds our small but remarkable planetary home.